Each year, firefighters run up the Sky Tower. Wow. Okay, this is supposed to be the Sky Tower, and this is firefighters running up it. That's exactly how physics works. But Lindley is preparing for this event by running upstairs in her building. Maybe they're neighbors with the Sky Tower, I don't know. Assuming there's multiple staircases. So each day she climbs to a height of 25 meters, and we're given some data about her training. Now, yeah, firefighting is very hard work. Have a few relatives that do it, and yeah, training like this, that's very impressive. So what data we're given? We're given the mass of Lindley and her equipment. So she's hasn't lost or gained any weight between the days, and she's climbed the same distance. However, in her second day, she shaved off 20 seconds, so she's already showing signs of improvement. In question A, we need to compare the work done and the power output by Lindley on both days. So they've given us some pointers to help us out. We should calculate the work done, calculate the power used on each day, and then don't forget we do need to compare them. So that's the key word in the question, comparing them. So a few ways to just break it down. Good. I'll do columns, because why not? So this way we can just show our working for day 1 and then pretty much copy it for day 2, but with the different values. And then at the end, we can make our comparison. So work done. So looking at the formula we're given, work done is equal to force times distance. Now, what is this force? So Lindley is climbing upstairs. So the force she is overcoming in going up is her weight force, right? That's what she's going against. So this force is actually her weight force, which is mass times gravity, right? Weight is mass times gravity, and we're given her mass as 80. So her weight force is 80 times 10. 80 kilograms times 10 meters per second squared, right? Acceleration due to gravity. And that gives her a weight of 800 newtons on both days. So that is the vertical force she is overcoming by climbing the stairs. So technically there's a few other forces like involved in her like muscles and things, but we're just zooming out and just looking at the big force involved here. So the work done is the force she's overcoming, right, to go up, times the distance upwards she goes, which is 25 meters. So 800 times 25 gives us 20,000 joules. So work is measured in joules because it is energy transferred. That's how much energy Lindley put in to get 25 meters upwards. For day 2, the exact same approach, force times distance, same force, and actually the same distance, right? 25 meters again. Wow, that was easy. Oh. So another 20,000 joules. All right, and what about power? So the formula we're given is power equals work done over time, or you might see it as energy over time, right? Because work is just energy transferred, so they're equivalent. But since we've just worked out work, let's use this notation. So the power output is the work done over time. Now we are given, well, we just worked out the work done as 20,000 for day 1. And in day 1, it took Lindley 50 seconds to climb that 25 meters. So 20,000 divided by 50 gives us 400. And then the units for power is either joules per second, or more commonly, we use watts. Comparing that to day 2, exactly the same steps, same work done, except she did it more quickly, right, in 30 seconds. So 20,000 divided by 30, just rounded to 3 significant figures, is 667 watts. Okay, so we've done the calculations, and now we need to compare them. So just by inspection, we see that the work done is the same in both days, but the power done, or the power output in day 2 is greater than day 1. So we just need to put that into a sentence and link it to the underlying physics. So the work done on both days is the same. Okay, I mean, that's pretty obvious. So why? Why is the work done on both days the same? This is because Linley had the same mass, right? Therefore the same weight force, and she climbed the same distance. So because Linley had the same weight force between the days, right? And climbed the same height. And that was, what was that distance? 25 meters. And her weight was 800 newtons. Right, so since work done is force times distance, and her weight stayed the same, and the distance stayed the same, the work done between the days was the same. All right, now let's compare power. So it was greater in day 2. So the power output in day 2 was greater than in day 1. Okay, that's obvious from the numbers. Why is this the case? So this is because what? The work done was the same? Okay, the work done was the same. However, in day 2, Linley did it much more quickly. So the work done over time was greater. In other words, the power. So however, she climbed the stairs in less time in day 2, or on day 2, which then results in greater power. Awesome. So that's a very nice excellence question for us. We laid out some calculations first, and then we compared them. But the bit a lot of students miss is just this bit here. Justifying it, for example, the same weight and same height, or same work, however, it was less time. So just link it back to the formula, but using our words. Linley's helmet fell off. That's no good. So it fell between the stairs. So if we're looking down, oh, that's a green highlighter. If you've ever been in a stairwell and you look down, you see it kind of spiraling down. So Linley's helmet, I don't know what fired helmets look like, but that just fell straight down the middle. Hopefully no one was standing at the bottom there. and she estimates that the helmet hits the ground at 20 meters per second. So using conservation of energy, assuming no other external forces or factors, what is the height from which the helmet fell? And we're given the mass of the helmet. And again, they've given us a few pointers to get us started in case we're stuck. So calculating the kinetic energy, and then, all right, it's got this kinetic energy as it hits the ground, but where did that come from? All right, it came from gravitational potential energy, and then how do we relate that to the height? So let's start off with what they suggest and calculate the kinetic energy of the helmet as it hits the ground. And we know kinetic energy is half times mass times speed squared. And we're given the mass of the helmet, 1.5 kgs. And we're given the speed as 20 meters per second, and that's squared. And so with that, we can calculate the kinetic energy as 300 joules. Okay, now where does this kinetic energy come from? Right, we have our beautiful helmet here, the ground. Hopefully no one's standing there. As it hits the ground, its kinetic energy is 300 joules. Assuming it fell, like it wasn't moving before it fell, up the top, its kinetic energy would be 0 joules, right? It's not moving. Which means its potential energy must be 300 joules, right? To equal the kinetic energy that it gains. And of course, on the ground, it has no potential energy. So we can say, so describing where this kinetic energy came from, so initially, so that's before helmet falls, it has 300 joules of gravitational potential energy. And we can say this because we assume there's no frictional forces, right? And we know gravitational potential energy is equal to mass times gravity times change in height. And we just said, all right, there's 300 joules of potential energy. And we know the mass of the helmet, 1.5. G is acceleration due to gravity, so that's just 10. And then height is what we're looking for. And so now we just solve this linear equation for height. So 300, 1.5 times 10, that's 15. And then we divide both sides by 15 to get height. So 300 divided by 15 is 20 meters. So if Lindley dropped the helmet from a height of 20 meters, it would accelerate and reach a speed of 20 meters per second as it hits the ground. Awesome. And then the final question is, all right, well, why will the helmet probably not reach a speed of 20 meters per second? Okay, so what do you reckon? So when we drop the helmet, yoink, what other forces are at play as it falls? Right, air resistance is the big one, which makes it lose or transfer energy out into heat and sound. So as the helmet, maybe it falls on its side here, as it brushes through air, these little particles are going to take some of the energy from the helmet, and that turns to heat. It's a very small amount, but it's still enough to reduce its final speed. So let's try put that into a couple sentences. So air resistance opposes the motion of the helmet. So that just means as the helmet falls down, air resistance acts against it upwards, right, in order to slow it down. This causes some of the air particles to collide with the helmet, taking away some of the helmet's kinetic energy as heat energy. And now since the helmet has less kinetic energy, the helmet will therefore not reach 20 meters per second, right? As it doesn't have as much energy as it thought it would. Not that the helmet can think, but you know what I mean. Yeah. And if you want a quick experiment to just observe this, just drop any type of bouncy ball and you'll see that the height it reaches upon return isn't as high as where you dropped it. And that's actually a great experiment to just measure energy losses. So I encourage you to try that one at home when you're bored. So maybe like right now. All right, see ya.